Let's proceed to the evening shift paper. 24th February JEE Mains 2021. And the first question: compare the rate of aromatic nucleophilic substitution. Mind you, this is nucleophilic, not electrophilic. What do I mean by that? On the benzene ring, you have electrophilic aromatic substitution and a nucleophilic aromatic substitution. Electrophilic aromatic substitutions are initiated by electrophiles, and their substitution, you see the Cl group. If this is present, this will be deactivating. NO2 group, if that is present, that is also a deactivating group, because these groups, they withdraw electron from the ring. But this is for electrophilic substitution reactions. So one might see that there are so many electron withdrawing groups, and then one might uh, think like the answer should be this is the least activated ring. But no, this is nucleophilic. And this, if this has happened with you, then my sympathies, but beware of the situation. Nucleophilic sympathy substitution. Nucleophilic substitution, how does this happen? Nucleophilic substitution you have seen in alkyl halides. So if you have a halogen and then there is a nucleophile, then the nucleophile attacks and halogen can leave. And this can happen in any order. That's why you can have SN1 or SN2. So you can have the nucleophile attacking and the halogen leaving at the same time, SN2, and nucleophile attacking after the halogen has left, then that is SN1. But here, if you remember, when you studied SN1 and SN2, you must have also studied that aryl halides don't give nucleophilic substitution easily. Aryl halides don't give nucleophilic substitution easily. And the reason for this is that this double bond in aryl halides, suppose this is a halogen, then the double bond in aryl halides, the lone pair of halogen, and you see this conjugation here, and you can understand that after making a few resonating structures, you can understand that there is a double bond character here at this bond. So halogen will not leave easily. Halogen won't leave easily. That's why nucleophilic substitution are difficult in this aromatic situation. With aryl halides, it's difficult to happen. But there is a very interesting kind of mechanism through Meisenheimer complex which can occur here. And as I see these electron withdrawing groups so many, I think this question is pointing toward that. So one way this can happen, one way nucleophilic substitution can happen with, let's say, chlorine on the benzene ring, is that the nucleophile attacks first, and chlorine will not leave easily, as we have seen before. So it attacks first, and then a carbanion can get formed here. This can happen in when, like, the attack is here on the phenyl carbon, not in case of simple alkyl halides. This can happen in aryl halides only. And then you see that a carbanion is being created, and nucleophile joins here, and then this minus charge through conjugation can move here, and then it can also move here. And then after this attack, this chlorine can leave, and then you can get back so from any resonating structure you can make it like this, and then you can have nucleophile here and Cl minus. So this is the intermediate here. This is the intermediate. It's a carbanion intermediate, but often it's called Meisenheimer complex. And this intermediate the stability of this intermediate will decide the rate of reaction, right? As in the case of other reactions, you can draw the energy, you can draw this kind of a profile, energy profile, and you understand if this thing goes down, this thing also goes down, because it has the reminiscence of this state here. This is a transition state, so it has a character, somewhat character of this state here also. So if this goes down in energy, this goes down in energy, and you see a faster reaction. So the stability of intermediate is important, and the intermediate is Meisenheimer complex, which is a carbon ion, which will get stabilized with these NO2s here. If you have an NO2 here, then this NO2 can withdraw this electron, right, through resonance. I can show it more clearly. So this is here, and NO2 group can be broken down like this. Sup, 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 minus, and this can move here, and this can go, the minus can reach till this oxygen. So if you have more NO2s, then more stabilization, and of course the best one here is this, and then this, and then, so 4321 is the right answer. You will have to go through the Meisenheimer complex to understand that. Then let's take a look at this second question. The reagent used to convert the following. So this is something which is getting converted into this thing, and what do you see here is that the carbonyl group here, this carbonyl group is getting reduced to CH2 group. So carbonyl group is getting reduced to CH2, and for this you must have studied in the aldehyde ketones chapter that you can either use Wolff-Kishner reduction, which is under basic conditions, or you can also use Clemmensen reduction. But mind you, there are double bonds in this molecule also, other double bonds. Here is a double bond, here is a double bond. So Clemmensen reduction, in Clemmensen reduction we use HCl and ZnHe. So this HCl can interact with the double bond, but it's funny that there is no option here, which could have been a good option to confuse students. Clemmensen reduction, it's not here. Then you have this is the condition for Wolff-Kishner reduction, in which you use an hydrazine, and you use a base, normally KOH, but here you have more better base has been used. This is ETO minus, which is even more better base than OH minus, because this minus is highly destabilized. So you have a better base. So same thing, this is Wolff-Kishner reduction, and this can do this job, because these reactants can't combine, can't affect the double bonds, because double bond is it attracts electrophiles, but NH2 is not an electrophile, because it has nitrogen with lone pairs. It could get attracted towards positive centers, right, and attack there. It's not an electrophile. OH minus is of course not an electrophile. It also has enough electrons, so it's not an electrophile. So that way you see that Wolff-Kishner reduction is a better answer here. Other reagents are picked up randomly, maybe. No, this red PCl2, this looks like this is also a reducing agent, but it will, I think, HI and red phosphorus is used as a very good reducing agent, but here is a Cl2. We already have an answer, though difficult to think what this can do with this molecule. Anyways, but NiH2 is a good option, because you can see NiH2 is used for hydrogenation, and it will affect the double bonds. It can also affect the carbonyl group. So all of these can get reduced. So don't use this, because you have to selectively reduce the carbonyl group. And NaBH4 attacks at the suppose you are thinking about the ketone part. So H minus, NaBH4 has hydride ions in it, so it reduces by hydride transfer kind of mechanism, and you will get an alcohol in such a case. So this hydride can attack here, this can move here, and then later on this can have an H from the solvent, and it can get reduced to alcohol, but not to alkane. So NaBH4, I don't exactly remember whether NaBH4 could reduce the double bond or not, but anyways, we have the answer right here. So Wolff-Kishner is the right answer. Let's move on to the next one. How many of the following amines can be prepared by Gabriel phthalimide synthesis? Now, what is Gabriel phthalimide synthesis? You know phthalic acid. Then you know phthalic acid amide. You have to think of phthalimide. So amide of phthalic acid. So if you take a CO and you do this NH2 here, and then you can see that very easily this can attack here, and the phthalimide should be like a double amide. You will get NH here minus H2O. So this is a phthalimide. And phthalimide, we start from phthalimide and we take a base KOH, let's say, and this hydrogen is acidic, because if it gets released, then the minus charge can be shared with these two oxygens here, as you can see. So phthalimide anion will look like this, and then you use an alkyl halide. So this nucleophile attacks here and this gets released. Very simple. And then you do a hydrolysis here. No, not here. Sorry. You see a delta minus here, you see a delta plus here, but there is more delta plus here. And this is more polarized kind of a bond. So hydrolysis here and here. So in hydrolysis, you have to just take an H2O molecule and see where is the delta plus, where is the delta minus, and attach respectively. You break this bond, and then you attach these two parts together. So you will get phthalic acid here, and hydrogens will get attached to this nitrogen. So you will get a primary amine, right? This is your Gabriel phthalimide synthesis. And remember that this is coming from the C is coming from this alkyl halide, right? From this alkyl halide. This alkyl halide, this C here, it gets transferred here. This C here, right? And there is a nucleophilic substitution involved here. So it could be SN1 or SN2 depending on conditions. So how to solve this question? We know the mechanism. Then we can think about this is a prime. All of them are primary amines. Very nice. All of them are primary amines, so all of them can be found. But let's think about this. The precursor alkyl halide here was this, right? And the reaction can proceed very nicely because the delta plus character here is very good. It will give a benzyl carbocation kind of a species if it goes through SN1. Not even if not through SN1, then still if it develops a little bit of delta positive charge, then that's fine. Here you see the precursor alkyl halide is something like this. And as we discussed before in this video, that aryl halides do not give nucleophilic substitution easily. And this is why I would like to go with this. Okay, how many of the following amines can be prepared? So this cannot be prepared by Gabriel phthalimide synthesis. And this one can be prepared if you use CH3Cl. This one can be prepared if you use CH3CH2Cl, right? This one cannot be prepared. So the answer should be 3 here. Out of these 4, only 3 can be prepared by Gabriel phthalimide synthesis. Okay, how about this one? Which of the following compound cannot be prepared by reaction of alkyne with HgSO4, dilute H2SO4? Okay, so this is oxymercuration. And reduction or demercuration, you can say. Oxymercuration, demercuration of alkynes. So let me give you a quick mechanism so that you can understand it nicely. Suppose this is an alkyne, and I would like to take something an unsymmetric alkyne, because this is what is going to be interesting here, because symmetric alkynes you can add anything on both the sides and you get the same result. So I will take, let's say, CH3C triple bond CH, and then I take Hg2 plus comes from the HgSO4, and it can make a pi complex with this molecule. So Hg2 plus will still be Hg2 plus, because it will use its own lone pair from maybe d orbital or something like that. But yeah, it has electrons, enough electrons to make this kind of a pi complex. No electrons given, no electrons taken by any species, so the Hg2 plus is Hg2 plus, and these carbons are still neutral. And then this is the carbon. Now one of these two bonds will eventually have to break, and you can feel that it should break with this side, because if it breaks from this side, the delta plus character will arise here, and Hg will get converted into Hg plus. So this is an electrophile, right? Because it has two positive charge, so it will like to have an electron. You don't think in terms of that this is metal. How is it accepting electrons? Mercury has a valency 1 also, I think. Yeah, so this will accept the electron, and then you break it up, and this from this side the bond should break, because here the plus charge will be more stable. But when this is happening from the other side, the water molecule, the solvent molecule, will also attack, and it will attack here, because here there is more positive charge. So the water attacks here, and get a double bond. You get Hg plus here. It accepts an electron. Okay, so then the H plus here, from here it gets removed. Hg2 plus also, this Hg can get released as Hg2 plus. So as a catalyst it came, and it will release itself as a catalyst, so it will release the electrons here, and hydrogen will release the electrons here, so oxygen will get neutral, and the H plus from here can get attached to this carbon, and you can see you get something like this, CH2. Okay, so notice this carbon here, which was susceptible of the positive charge, which can be more substituted, or it could be benzyl or allyl, something like that. This is the carbon where the OH has been attached. I like to call it as a CS or CP. This is the special carbon. In the double bond also, and in the triple bond also, we should understand that one of the carbon is more capable of handling the positive charge, so that is special. And here this carbon is this one, and then you see it's an enol, so you see the double bond will get here, and the hydrogen can go there, and keto form, so keto enol tautomerism. So you get to the keto form, and you get the final answer like this, acetone. So what happens is the ketone or the carbonyl group is formed at that carbon where which was more capable of handling the positive charge. So if we think of this CH3CHO, we will have to work backwards. So CH3CHO, you can think like this, and you can think of the enol form, go backward. So the enol form was this, and then you can go backward to understand the starting alkyne was this. So it can be prepared, this thing can be prepared with this reaction. You can see this is the starting alkene. Now let's see CH3CH2CHO. Okay, let's go backward to the enol form, CH3CH double bond CHOH H, and what you see is that the alkyne, if you go back to the alkyne, you see you will get this alkyne. But wait a minute, in this case the alkyne was symmetric, and the OH can add any side. But here, if you do this kind of a reaction with this mechanism, cyclic intermediate, you know that the OH should attach itself at this. We use the same thing here, the same example, right? So we know that this OH should attach at this carbon, not at this carbon. So when you get back to the alkyne and you work forward and you think at this step, it doesn't feel right. So this one cannot be formed. Which of the this is it. This is the answer. If you want to try the third one, let's try the third one also. Third one. The third one, you have CH3, C double bond O, CH2, CH3. Analyze it. You can analyze it in two ways. Maybe you can go like CH2, CHOH, and CH2, CH3, and CH3, COH, double bond CH, CH3. And then if you go back from here, you see this alkyne here, CH and CH2, CH3, and you see this is the carbon which is more capable of handling the positive charge, and the OH is coming here. So this from this way you can reach this. What about this one? And now you see that CH3, C triple bond C, CH3. Okay, this is a symmetric alkene, so whichever side you add the OH, it doesn't matter, and you can also from this alkene you can get to here. Interesting. So both of these options can lead to this compound right here. Let's check the fourth option also. I like to work backwards. Let's take the fourth option, and you can analyze it in two ways. And here is a hydrogen, so you can have this form as enol. And then if you see, this is a double bond, and then if you see there is no other hydrogen here, so you can't make a triple bond from, you can't go like this, right? Because carbon will have 5 bonds, so this is not possible. Let's analyze from the other side. Okay, this could also be true, but we have another side to analyze from, and from this side you go backward and you go backward and you get this alkyne. And now you think, if water is getting added on this alkyne through this oxymercuration mechanism, then this is the CS. This is the carbon which can handle the positive charge better because it has an alkyl group attached to it. So this is where the OH should come, and it comes here. Okay, so this can be prepared by taking this alkyne, right? So yeah, second option is correct, no doubt about that. Let's move on to the last one. Diazonium salt of which of the following give colored dye on reaction with beta naphthol? Diazonium salt. Okay, diazonium salt, like we know that with aniline we can form a diazonium salt if we use NaNO2 and HCl, and that diazonium salt has a structure like this. But if you remember the mechanism, you need these two hydrogens here for this to happen, for diazonium salt to get formed. So in the first example, you don't have this is a secondary amine. So diazotization can only be done with 1 degree amines, right? 2 degree amines, they stop at nitroso derivatives and nitroso amine, and 3 degree amines they can't even proceed as far as I think, because this reagent here, it gives you this ion NO plus, nitrosonium ion. Pretty interesting, because nitrogen positive has only made 2 bonds here. But anyways, if you have a tertiary amine, then you have something like this, and this is an electrophile. It can attack here, and you can get something like this. But then this nitrogen will be positively charged, and then there is no hydrogen to be released from any of the sides, so it will attach and then it will go back also, because this is not a very stable compound. So it will go back and give these two things back, and nitrosonium ion generated will also go back by equilibrium to NaNO2 and HCl which is actually HNO2 acid in situ, which will go back to all these things. So the 3-degree amine can't even react, so no reaction. Yeah? And 2-degree amines will reach till N-nitrosamine. This can be I mean, anybody who is preparing sincerely would know about these things. 1 degree amine will give the diazonium salt. So only two options here remaining, which could be the answer, right? And which of them is correct? So what happens now? Uh, if you get from this, you get a diazonium ion like this, and from this you can get a diazonium ion like this. But this diazonium ion wouldn't be very stable because it will naturally make N2 and a very good carbocation like this, CH2 plus and N2. This will not break down very easily because then you will get a phenyl carbocation and nitrogen. So this can be made stable under 0 to 5 degrees C temperature, and then you can use this thing without the nitrogen leaving this whole diazonium ion as an electrophile, and you can make it to attack on the beta naphthol. And beta naphthol is naphthalene and alpha beta here, the alcohol, and it can attack at one of the activated sites wherever it can, and you can get a colored dye in which you will get extended conjugation. So I think you will get a final product something like this. I think this one is activated. Let's break it down a little bit. This is your OH group, and here so the lone pair can get transferred to here, which can, and the double bond can go here, and this can go here. Yes, this position is activated. So this position, at this position you can join it because steric hindrance is lesser here, and you get, and you see because of this extended conjugation, from here you have double bonds here, and then there is an alternate double bond here, then there is an alternate double bond somewhere here. So you see extended conjugation, and that's why this molecule will be a dye. If you want to know about this extended conjugation and what dyes are, so I have a video on my channel about phenolphthalein molecule, and in that I explain how extended conjugation can result to color. So you see extended conjugation and you will get a colored dye with this thing, not with this thing, because this will very easily dissociate into CH2 positive, and the CH2 positive, if it gets attached to the beta naphthol, that is also an electrophile, fine, but that will give you this CH2, and you wouldn't get any extended conjugation with this CH2 in here. If you have this kind of a group, then you see this the conjugation of this ring can get extended to this ring and this ring and so on. So the fourth option is correct here. I think this is the last one. Thank you very much. Have a nice day.